I wanted to mention that all of this stuff that I've talked about in the past 2 days at least is extremely new. So new that I don't have slides yet because I haven't actually written it down on paper yet. There are a lot of open questions. You know, can this be used for getting nicer bounds on random matrices? Like, we haven't looked at that at all. I would love it if, you know, people took it and tried to use it as a tool for understanding things. We find in particular that it's very useful computationally, especially if you're doing normal free probability. It turns out to be much easier to take two distributions and find a new distribution using this finite method than to have to go through the rigmarole of, you know, doing free things. And we already know that it has had some success in various areas, and so that's one of the things I'd like to talk about today. So this is joint work with Dan Spielman and Nikhil Srivastava. Okay, so let me talk about expander graphs. So expander graphs are sparse, regular, well-connected graphs that approximate random graphs. What do I mean by approximate? It means that it has these properties that sets of vertices have many external neighbors, or otherwise very few internal neighbors. There are no small cuts, so if you take the vertices and divide them into two sets, there will be a ton of edges going in between them. Random walks mix quickly, and in theory, you can get from A to B using very few edges. So there's almost always a direct path from one vertex to another. You don't have to sort of meander around the graph in some bizarre way. And these are used throughout computer science. They're the basis of error correcting codes. They're the basis of pseudorandom generators, and they've also contributed to probably two of the biggest results in computational complexity of the 2000 decade, the PCP theorem and SL equals L. So there are different types of expansion. There's edge expansion and vertex expansion. I'm going to be concerned about spectral expansion, primarily because it's one of the only ones that you can actually really get your hands on. The other two most of the problems are NP complete. But for constant degree graphs, these are interchangeable up to a constant. So I'm going to use the adjacency matrix. If you're used to the Laplacian, this is the Laplacian, except the minus the Laplacian with the diagonal zeroed out, where Aij is 1 if and only if Vij is an E. And here, since the graph is D-regular, all of the rows are going to sum to D. So since A is symmetric, it has all real eigenvalues. Since the rows sum to D, 1 is an eigenvector with eigenvalue D. And if G happens to be bipartite, then minus D is an eigenvalue as well. And you can't get rid of these. These are sort of a penalty that you pay for being a finite graph of degree D. So we call those trivial eigenvalues. Now, G is considered to be a good expander spectrally if all of the non-trivial eigenvalues are small in absolute value. So for example, the complete graph has all non-trivial eigenvalues of -1, and the complete bipartite graph has all non-trivial eigenvalues of 0. The problem is that we need big graphs with small degree. So these are small graphs with small degree. We can usually get big graphs, or they could be big graphs with big degree. But we need big graphs with small degree. In particular, we would like infinite families of such graphs. So what can we possibly hope for? So there's a theorem by Alon and Bopana that says for every epsilon greater than 0, there is some n such that eventually every d-regular graph on n vertices has non-trivial eigenvalue greater than 2 square roots of d minus 1 minus epsilon. So essentially, 2 square roots of d minus 1 epsilon, minus 2 square roots of d minus 1 to 2 square roots of d minus 1 is the best that you can possibly hope for asymptotically. And if you can actually find an infinite collection of graphs which stays in this region, they're called Ramanujan.
And this is the best that is possible because in the limit you have the continuous band, the band of continuous spectrum from this. This is the band of the continuous spectrum.
Yes, but I'll be there in 1 second. So we will call an infinite collection of d-regular Ramanujan graphs a Ramanujan family. So a brief aside, recall that expander graphs have this property that sets of vertices have many external neighbors. So in this sense, the ultimate d-regular expander is the d-regular infinite tree. Okay? All eigenvalues of the d-regular infinite tree, as you said, lie in this interval minus 2 square roots of d minus 1, 2 square roots of d minus 1. So if this number looks completely bizarre to you, like why 2 square roots of d minus 1, this is why. The infinite tree sort of defines this domain. So being Ramanujan can be seen as a good finite approximation of a d-regular infinite tree. So this is what we're trying to do. And I should say right here, this now sort of almost begs to be, this is in the framework of all the things that I've been talking about, right? So a d-regular infinite tree is the Cayley graph of the free group on d elements. We're trying to find some finite approximation of this free acting thing. And so the question is, can we actually find one that does better than what the infinite version is? Or can we find a collection of them? So previous results, so a theorem of Margulis, Lubatsky, Phillips, and Sarnak separately showed that Ramanujan families exist for d equals p plus 1 where p is a prime number. And this was sort of a tour de force. It brought together 3 areas of mathematics, very deep results in real algebraic geometry, results in number theory as well as representation theory, and really was quite an achievement, actually. And the proof depends very heavily on these algebraic techniques. They essentially show, they pick some group, and then they show that a Cayley graph defined by that group is Ramanujan. So an open question for a long time was, are algebraic graphs the only families? And we know the answer is almost no. So Friedman in 2008 showed that if you randomly just pick a d-regular graph out of nowhere, then with extremely high probability, it has its non-trivial eigenvalues in the interval minus 2 square roots of d minus 1 minus epsilon and 2 square roots of d minus 1 plus epsilon. So you can always get very close. But the question is, can you actually sort of always, find things that are over the edge? So are Ramanujan families special, or are they just everywhere? And I want to prove, and my goal is to show, so previously we showed that actually there exists Ramanujan graphs of all degrees. This time I would like to show that there exists Ramanujan graphs of all degrees and all sizes. So last time, essentially, in order to produce these things, we needed to do this operation on graphs, which caused us to duplicate the graph and then sort of connect the edges in some pseudo-random way. And that caused the number of vertices in the graph to double every time that we needed to get a new graph in our family. In this version, we would like to show that you can build one of any size and any degree. And the nice part about this is I think that it goes much better with this idea of how free groups are sort of generated. So I've already been through all of this. OK. So the idea is that we're going to start with some Ramanujan graph. So it has all good eigenvalues. And you can think of that as sort of an approximation of the free group on d minus 1 elements. And we want to add another element. So we want to now have a free group on d elements, which in our respect corresponds to adding a matching. So a matching in the graph. And this is the characteristic polynomial of a matching. Okay, x minus 1 to the n over 2, x plus 1 to the n over 2. And here's another matching. So we could add this matching, we could add this matching. The problem is some of the matchings are going to give us, not so great new graphs. Others might give us better graphs. So how are we going to do it? We're going to pick a random matching. The way we're going to pick this random matching is by using polynomials. Okay, so we're going to consider the p of x, which is the expected polynomial, this expected characteristic polynomial over all of the possible matchings. So the first step is to prove that p of x is real rooted. The second step is to prove a bound on the largest root of this polynomial. So we're going to throw away the top root and prove the second root is smaller than something. And then the idea is to prove that these polynomials form an interlacing family, which then implies that there exists some assignment of these m1 through md, whose polynomial does better than the expected polynomial, and therefore these things do the job. OK. So the formula for the expected polynomial, if A and B are symmetric matrices that for which one is an eigenvector, well, so that all the columns sum to the same thing and all of the rows, then the characteristic polynomial of A is some x minus A times some other p of x. And the characteristic polynomial of B is some x minus B times some other q of x. And what you get is that if you take the expectation over all permutation matrices of A plus pi B pi transpose, what you get is the n minus 1 convolution. So what is this saying? This is saying that this collection of permutation matrices is acting as a quadrature set for taking the integral over all unitary matrices.
A and B any symmetric?
A and B are both symmetric.
Well, characteristic polynomial of graph, yes? That's
Oh, sorry. OK. So our theorem is that if AN is the group of symmetries of a regular simplex centered at the origin, then doing this expectation over the pi over all of the permutation matrices is the same as doing the expectation over all of the orthogonal matrices. And we know what this is. This is this finite convolution. And I should say that this depends so this is not true if A and B are not orthogonal to the all ones vector. This depends on the fact that they're orthogonal to the all ones vector. But there are different things that there are different quadratures you can do in the general case. OK, so why would quadrature even work? Well, we know that it works in other cases. Gaussian quadrature in particular works on the circle. So when you integrate over from 0 to 2 pi, you can actually do that by just summing over the node points of the roots of unity. So we're going to actually have to do, instead of going over the circle, we're trying to integrate over the simplex. And the idea is to show that essentially where I started from is irrelevant, right? So if I show that some f of ab of pi, an expectation over the an, is the same as the expectation of that pi plus some small rotation, where that rotation is general, then what that means is that this thing didn't depend on the initial rotation in the first place. So in particular, we need to show that flipping, well, essentially all of the operations in D3 are invariant under this expectation. And then what we need to do is show that all of these things generate the entire group. So we're going to show that each face does the things that we need to do, and then the idea is to show that the collection of operations on each of the faces then generates the entire group. this is just re-saying what I've already said. Then for symmetric matrices A and B, we can get, we can solve this actual thing by just taking the free finite convolution that we've talked about before. And what's important here is that when P and X have real roots, then this free finite convolution has real roots as well. Otherwise, it's hard to make comparisons between roots. OK, so what is this expected characteristic polynomial? Well, each individual polynomial looks like this. And so when you take the expectation of adding a number of different matchings, what you end up getting is x minus d times the k-wise convolution of this polynomial. So essentially, we're going to start with an empty graph, and then we're just going to keep adding matchings. And the whole point here is to really imitate what happens in real free probability. So in free probability, when you have distributions mu and nu, and a sequence of symmetric matrices A_n and B_n whose eigenvalues distributions approach mu and nu, then you can form this convolution, which turns out to be the limiting eigenvalue distribution of A_n plus a randomly rotated B_n. The problem is that we need it the result not only for finite things, but we then also have to produce or at least show the existence of something that does just as well. So when you do this in the infinite case, you have to use the R transform, and in that case, you have this equality here. This alpha max is really just the R transform. And when we do it in free finite convolution, this is something I showed yesterday. The equality that you get in the infinite case becomes an inequality in the finite case, which is actually something that helps us. So for the root bound, and the other thing, I mentioned this yesterday as well, the R transform is actually a formula which you can consider to be the behavior of the largest root under perturbations. Right, so if you have G inverse of x equals W, this means G of W equals x, which means P prime of W which means P of W minus 1 over xd. So the value of G inverse, which is essentially the value of the R transform, you can think of as the largest root of P when you apply this 1 minus 1 over xd partial operator to it. And what's nice about this is that it's much smoother than what you would normally do with, when you combine two things and get a new root. When you combine two things and bound the largest root, here, because we're doing it over and over again, it turns out to be better to have this kind of smoother averaging. OK, so then you essentially just plug into the formulas that we have, and you can show that the answer is 2 squares of d minus 1. OK, so now we've shown that the expected characteristic polynomial, or the expected polynomial, behaves the way that we want. We now need to show that this thing forms an interlacing family so that we can then assert that one of these things does as well as the others. And again, this is going to use interlacing. And in particular, common interlacing. So this, and what really common interlacing is doing is it's separating out the roots from each other. So all of these roots are bundled together, all of these roots are bundled together, and all of these roots are bundled together. And as I mentioned yesterday, if P1 and P2 have a common interlacing, then one of them has a larger second root than the expected one, and one of them has a smaller, or at least one. And if you don't have a common interlacing, everything goes awry. You can just, you can get essentially things without roots. You can get things, well, they always have roots. You can get things without real roots. You can get things where the real roots are way off to the side. Everything goes wrong. So just a reminder of yesterday, we'll call a collection of polynomials an interlacing family if when you put all of these polynomials at the bottom of the tree, then essentially at every node of the tree, the children of that node all have a common interlacer. And the theorem is that if you have such an interlacing family, then you have a comparison between the leaves of the tree and the top of the tree. And actually showing that finding these interlacers, we never actually find them. There's actually a very nice theorem that says that such an interlacer exists if and only if all of the convex combinations of the polynomials are real rooted. And so rather than having these separate conditions of real rootedness and interlacing, everything sort of gets reduced down to a bunch of real rootedness statements. Okay, so our interlacing family is actually fairly complicated because these random permutations do not act particularly well. But this is our expected, so this is going to be the top of our tree, this expected polynomial over all possible permutations of these matchings. And the idea that we're going to use is to use random swaps. So a swap is going to switch sigma ij with probability lambda and is going to keep everything the same with probability 1 minus lambda. And the idea is that you can then write a uniform random permutation as a product of these random swaps with different probability distributions. And the nice thing about the swaps is that they are essentially a rank 2 perturbation, which means that they will have a common interlacer. Because all rank 1 perturbations have a real interlacer, and so the perturbation which is in between this rank 2 one will have this same perturbation, the same interlacer. Right, so both of these will interlace. The issue is that as we now move up the tree, we're not going to be able to write these things as determinants anymore. So at the bottom of the tree, it was nice because we could write them as a determinant of blah. This was a characteristic polynomial. When you then start averaging over these swaps, you lose the fact that this is a characteristic polynomial of something. But what ends up happening is you still lie in this larger class, which we call determinant-like polynomials. So essentially, the only thing you need from all of the things that we're getting from the characteristic polynomial are the fact that it's hyperbolic, which means that it's real rooted as a polynomial in T, and that when you do a rank 1 update, this is linear in S. Right? Those are the two properties we're using. And so we'll essentially, even though we're leaving the realm of characteristic polynomials, we're going to stay in the realm of polynomials which do these two things. And of course, at the beginning, the determinant is obviously determinant-like. And what our theorem is that if P is determinant-like, and then you do one of these random swaps to it, that's determinant-like as well. So you maintain this determinant-likeness all the way up, which means that you can keep performing the operations. OK. So in the end, let me review. How did we do this? We defined this expected characteristic polynomial by summing over all of the permutations of possible matchings. We then proved that P of x is real rooted by essentially computing out this polynomial and then applying, using the convolution, and then applying the fact that this thing preserves real rootedness. And then we proved that the second largest eigenvalue is less than square root of d minus 1, 2 square roots of d minus 1, using our free finite convolutions. And then we proved that there's actually a relationship between the things that were used to make this expected characteristic polynomial and the expected characteristic polynomial itself by showing the interlacing family and showing real rootedness. And that required us to use these determinant-like polynomials. So some questions. What about non-bipartite Ramanujan graphs? So we've cheated in a little bit. So as you can imagine, or at least when I told you the definition of Ramanujan graphs required you to bound the roots both below and above, right? And everything that I've mentioned to you in the past 3 days can only bound one root. And that's the truth. We can only bound one root. But it turns out that with bipartite graphs, the spectrum is symmetric. So if you bound the top root, you're also simultaneously bounding the bottom root. So that's sort of our way of cheating into getting 2 roots for the price of 1, essentially. We don't know how to get 2 roots for the price of 2. That would be an extremely interesting thing if we could start bounding 2 roots at the same time. Are there further extensions of free probability? I think this particular use is the first one that you can sort of directly see was inspired by the way that free probability works. The third question is whether there are efficient constructions. Right now, all of the results using this method of interlacing polynomials is completely existential. And there have now been a number of them. So in particular, there's a new proof of a better bound on traveling salesman problem, which uses this type of construction. And it has very much, I think, annoyed the computer science community because they've shown that we now have this algorithm for solving this problem, but we can't actually give you the algorithm, right? Like we know that, essentially we can compute some estimation of what the TOR is, of the total cost of the TOR, but we can't actually give you the TOR. We just know that it exists. And then the last would be whether we can get explicit constructions for these things, like, so the nice thing about the Lubatsky-Phillips-Sarnak constructions is that they are actually constructions. Like you can write down what it is, and they're actually not very complicated at all. Alex Lubatsky famously says that he can explain how to build Ramanujan graphs in about 1 class period, but it takes him 2 semesters to actually show that they are actually Ramanujan graphs. So at least in that respect, all of the hard work goes into the analysis. And that's it. Thanks.